All right, well, moving on, I want to talk about a concept you're probably already familiar with. I'm guessing you've heard of the pH scale. You may have heard about things being pH balanced, which means it's pH neutral. But the pH scale is used to identify how acidic or how basic a substance is. That term basic, you may also hear that referred to as alkaline. So when you're talking about how alkaline something is, it's just another way it's synonymous with how basic is it, how strong is the base in the solution. And so the reason it's called the pH scale is that pH stands for potential hydrogen. Whoops. And that should now make sense to us because we understand that acid-base reactions have to do with the donation of hydrogen, right? A hydrogen ion. Specifically, the pH scale is a measure of the presence of the hydronium ion. And so you don't have to know how to do this. I just want to show you an example here. Like this is not, I won't give you a problem necessarily where you have a reaction like this. But notice in this reaction here, the result here, this is our acid, this is our base. And the result is this hydronium ion is produced. And so it turns out anytime you have an acid with water, and if acid is in a solution, there's going to be water present, this hydronium ion will be formed. And so the presence of that hydronium ion is actually how we determine the pH of a substance. And the scale runs like this. The scale is from 0 to 14. And basically, if it's 7, it's neutral. All right, neither acidic, whoops, if I could spell neutral, neither acidic or basic. All right, if it's below 7, is acidic. Now, the lower the number, let me just write lower means more acidic. And then, of course, as you would expect, above 7 is basic. And the higher the number, the more basic the solution is. All right, so if something's got a pH of 1, it's very acidic, right? If it's got a pH of 5.5, it's still acidic, but it's not as acidic as that one that had a pH of 1. And then, of course, on the base end, if you've got a solution that has a base that has a pH of, say, 8, then it's going to be basic, but it's not nearly as basic. It's a really strong base if it's got a pH that's up there closer to 14. All right. So just make sure you know that scale and know where neutral is. Like I said, this is what we refer to as pH balance. You know, some like kids shampoos and things like that will say pH balance because they won't burn your eyes because they're pH balanced. So that's what that means. It means it has a pH of 7. Okay. So I want to talk about acid-base neutralization now, and the best way to understand this is just to do an actual example that we have in the book. And the example in the book talks about one of the main ways that we're familiar with acid-base neutralization. If you've ever eaten Tums or some milk of magnesia or taken something like that to kind of settle down stomach acid, what you're doing is you're trying to neutralize that excess stomach acid that your body's producing and making you feel sick. So this problem actually is based on that idea. And so basically, here's what when you hear acid-base neutralization, all that means is there is a chemical reaction taking place between an acid and a base. And the goal, if your stomach's overproducing acid, the goal is to have enough of that base so that the acid and the base fully react with one another and the acid goes away, right? So it's all neutralized. That's the point. And so when you look at these problems, words like neutralization. The next set of problems we look at has this word titration in it, but really the idea is the same. We're just doing the same stoichiometry stuff that we've done in the past, where we're trying to see if we've got a certain amount of one substance, how much of the other substance is going to be needed for everything to fully react. All right, so just understand this isn't really anything new, other than the fact that we're dealing with acids and bases now, and so how that works is new, and we're going to understand how to build the chemical formula now that we know how acids and bases tend to react with one another. But I'm going to do example 11.5 just to kind of walk us through one of these problems. And this one is exactly the situation I just described. Your stomach produces hydrochloric acid, HCl, that's used in the digestion of food, but sometimes it overproduces hydrochloric acid. Antacid tablets, like Tums, are meant to neutralize the excess HCl that comes from the overproduction. So if a stomach overproduces 84 milliliters of a 0.1 molar solution of HCl, how many grams of magnesium hydroxide, MgOH2, which is an active ingredient in some antacids, would be necessary to neutralize it? So in order to do this, the first thing we have to do is we have to write down the chemical equation, okay? And we now know how to do that. If you'll notice, so we've got HCl that's combined together with this magnesium hydroxide, right? MgOH2. And we notice this is an ionic base, and we just got through doing some problems in previous video where we discovered that when you have an acid react together with this ionic base, it produces water and it produces a salt. And what is a salt? A salt is the ionic compound that's formed from whatever's left over whenever the water is made, right? When the water is produced. And so if we look at this chemical reaction here, the H that's donated by the acid combines with the OH that's in this to form the H2O. So what's left? We have Cl and we have Mg left. And so that's what's going to be our salt over here in this part of the reaction. And so we just have to do swap and drop with Mg and Cl. We always put the metal first whenever we're writing these ionic compounds. And magnesium is in column number 2, right? If you look at your periodic table, so that's going to have a 2+ charge as an ion, and Cl is in column 7a, so it's going to have a 1- charge. So we're going to do a 2+ there and a 1- there. And so when we swap and drop this guy, we're going to get MgCl2. So that's going to be the ionic compound that's produced over here. And then we just need to make sure it's balanced, right? We see we have 2 Cl's on this side, so we need to put a 2 in front of this guy to give us 2 Cl's over here. How are we looking on the oxygens? We've got 2 oxygens on the right side here. So we need a 2 here. That's going to give us 4 H's, and we've got 2 H's from here and 2 H's from here. So the H's are balanced. Looks like we have the correct number of magnesiums as well. So I think this is balanced. I think we're good to go. Yeah, just a 2 in front of the HCl and a 2 in front of the H2O. Okay, so now what they told us at the beginning of the problem was that the stomach overproduces this hydrochloric acid. And how much does it overproduce? Well, it produces 84 milliliters of hydrochloric acid. And it is a 0.1 molar solution of hydrochloric acid, all right? Now, why do we need this? All right, so here's our goal. The question is, how many grams of MgOH2, how many grams of this will be necessary to neutralize this amount of HCl? Well, what do we need to know in order, if we have one substance, what do we need to know about that substance in order to figure out the number of grams of another substance in a balanced chemical equation? Remember our little path, our stoichiometry path that we take, right? So if we start with grams of one substance, we can calculate the moles of that substance. Once we find the moles of the substance, we're able to calculate the moles of another substance in the chemical equation, and then we can get the grams of that second substance if we need to, right? So in this case here, what we're going to do is we're going to follow this portion of the path, right? Where this is our substance A and this is our substance B. And so we're going to use this information here to calculate the moles of substance A, and from there we should be able to eventually figure out the grams of substance B. Well, how do we do that? We do that with the formula that we learned in our solutions chapter, right? They've given us the molarity and they've given us the volume of hydrochloric acid. And so if we have molarity in the volume, we should be able to figure out the number of moles using the molarity equation, right? So remember, the molarity equation looks like this. Molarity equals moles over the volume. The volume is in liters. So we're going to rearrange this guy to solve for moles, and moles will equal molarity times liters. And so that's going to be 0.10 molarity times. They gave us the amount of hydrochloric acid in milliliters, so we're going to convert that to liters by simply moving the decimal place 3 places to the left. And so we get 0.084 liters. And when we multiply that together, we're going to get a value of 0.0084 moles of hydrochloric acid, right? All right, now we know the number of moles of substance A, this one here. We should be able to just convert from moles of A to grams of B. And so let's make sure we remember how to do that. We'll start off with moles of substance A, which is our hydrochloric acid. And we're going to multiply that times the relationship in moles between the hydrochloric acid and the magnesium hydroxide. According to the balanced chemical equation, there are 2 moles of HCl for every 1 mole of Mg. And so we're going to do 1 mole of MgOH2. I said Mg a second ago, but I meant MgOH2 over 2 moles of HCl. There we go. I'll get it right in a second, right? So that's going to cancel out and leave us with the moles of MgOH2. And then we're going to multiply that by the molar mass of MgOH2. So that we can calculate the number of grams that represents. So we go to our periodic table, we look up the atomic mass of MgOH2 to get us the molar mass of that. And when we do that, we find out that it is 58.33 grams of MgOH2 per mole. All right. So what we're going to do now is we're going to put 58.33 grams of MgOH2 on top. And on the bottom, we're going to put, that's what 1 mole of MgOH2 is equal to, right? And so we plug all of that in our calculator and we get a final value. I'm going to write this down here just to make sure we've got room to see it. It's going to be 0.24 grams of MgOH2, like that. All right, so that's our answer. And so here's what I want you to understand. Other than having to write this balanced chemical equation, right, at the very beginning, because they gave us the acid and the base, and so we had to write the entire balanced chemical equation. But once we did that, we're really just doing problems that we've already done before. We've done problems in the solutions chapter that involved molarity, and we even did problems like this that involved molarity, and then you had to end up finding the moles of a substance that was in there or the grams of a substance that were in there. So really, all of this from down here is stuff that we've done in previous chapters. The only thing new to this chapter was being able to write that balanced chemical equation. So nothing crazy, nothing that you haven't seen before. Hopefully that'll help you feel a little bit better about the content that's in this chapter. And really this is going to be right in line with what we're going to be talking about with our next topic, titration, but we'll save that for our final video. Okay.